Now, I wanted to make sure that the people that actually did the work get accredited. And most of this work was done by the students, Dumitru and Jonah, and Hayu, who's a postdoc in Spain now, and Jabin and Aaron, who are also postdocs. I'll be mostly talking about work done by Hayu and Jabin, and by, of course, these people below who are more senior, and then at the end get to some new work that's done by Jonah and Dumitru. Now, I'll be talking about flat bands, and there's two ways of thinking about flat bands, and these ways are related to whether the flat band that we're looking at, where the Fermi level is, has got a large gap to other dispersive bands, or not. And large meaning large by as you know, with respect to the interaction. So in the way that's treated in most current or up to current, or almost in all strong coupling flat band theories, is the interactions are treated by projection to the flat bands. And this is basically a paradigm where the gap between the flat band and the dispersive bands is much larger than the interaction. And the interaction is also, however, larger than the dispersion of the flat band. The flat band might not be exactly flat, might have some dispersion, but the interaction is larger than that dispersion, but much smaller than the separation to the next level of dispersive bands. In that case, you can just take your physics and project it to the flat band, and this is how you get things that we all know and love. For example, I don't know, 10 years ago, fractional Chern insulators, fractional topological insulators, etc. And this is also how you get basically the quantum geometry of the flat band. Once the flat band is flat, you don't have any kinetic energy. If you projected your interactions into the flat band, you basically have no energy scale in the problem. Certainly no kinetic energy scale. And the only thing that's important about the flat band is its quantum geometry, or its, i.e. its wave functions. And then you can see that basically in this first way of projecting the interaction to the flat bands, remarkable things happen, and these remarkable things were highlighted by Päivi Torma. You can look at her talks on the web, where basically you get, you know, collective modes that have stiffness that are basically related to the quantum geometry. So that's one set of one way of treating flat bands with interaction. But however, is not the only way, because in a lot of the physics problems, and certainly, for example, in twisted bilayer graphene, or some other problems such as the Lieb lattice, for which there is no separation between the flat band and the dispersive band, the dispersive bands are much closer to the flat band than we would like for a full projection. So if I want to look at the interacting problem of flat bands plus dispersive bands, where these dispersive bands are not that far away from the flat band, and now add interactions that are not smaller or are comparable to the gap between the flat band and the dispersive band, then I cannot just do the projection, or, you know, there might be cases in which projection might work well enough, but it's not obvious why you should do the projection. And here I claim that another paradigm comes in, and this is what I want to talk about in today's talk. And this paradigm is that of mapping these Moiré systems to or these flat bands with a small separation to dispersive bands to a heavy fermion problem, and in particular, it's mapping to a topological heavy fermion problem for reasons that I'll explain in a bit. So the case that I'll be looking at is twisted bilayer graphing, but I want to make the case that there's a bigger paradigm at work. Now, in twisted bilayer graphing, the following things happen. You twist by a small angle, and instead of having Dirac cones, you find that at special angles, you have flat bands. And these flat bands are flat to within 10 milli-electron volts, so they're very flat. And there's two quantum numbers that come in, and the quantum numbers are that of spin and valley. Valley meaning that the K electrons of the lower layer and the K electrons of the upper layer that's been twisted by a very small angle from the lower layer form one valley, and the K prime electrons of the lower layer and the K prime electrons of the upper layer, also twisted by the same small angle, form another valley. And these valleys don't communicate. At the single particle level, hence there's a degeneracy of 4, and you get two flat bands. And these flat bands, each of degeneracy 4, can be hence populated by 8 electrons, 2 times spin, 2 times valley 2, 8 electrons. And we're going to count the electron number from the from this gap, this single particle gap. We're going to say this is minus 4 electrons. This single particle gap is plus 4 electrons. And in single particle, hence filling the system with, 1, 2, 3, up to 4 electrons of -1, -2, -3 should be a metal, right? So in filling the systems with electrons in integer filling should be a metal. But of course, as we know, this is the experimental plots. This particular one is from Efetov's group. And what they see is that integer filling of these flat bands, you basically get insulators. And in transport, these insulators, for example, at filling 0, are not that clear, but in STM they are. So local experiments see a large gap there, local probe experiments. So we're going to take the view that you've got correlated insulators, at least at some scale, in these at the integer fillings, and remarkably superconductivity around them. And hence this is obviously a case that interactions need to be taken into account to understand the physics of the system. What complicates the picture is that it turns out that these flat bands, so 2 per valley per spin, are actually topological. So in that sense, you cannot form a local description of them. If I could form a local description of them, I could just, describe them in terms of localized orbitals. I would have a Hubbard interaction or some sort of Coulomb interaction in those orbitals, and the physics would be much simpler since there's no kinetic energy or very small kinetic energy. But these bands are actually topological. And some of these insulators here that are staying at, integer fillings, for example, the one at filling 1, are Chern insulators, correlated Chern insulators, in the sense they have a Hall conductance, which spontaneously develops. And that's clearly the result of both topology and interaction. So you can't discard the interactions, you can't discard the topology. So how do you take both of them into account? Well, to puzzle us even further, there's clearly a contradiction between two sets of experiments in twisted bilayer graphing. Some experiments suggest the existence of local moments. You go do some STM, you find out that the charge is heavily localized on what are called the AA regions of the Moiré lattice. These are the regions of the Moiré lattice where the lower graphing lattice and the upper graphing lattice have A sites on top of each other. And there's not much charge density at the AB sites. You can clearly see it here. Now, the charge density forms a triangular pattern, even though you started with a hexagonal lattice, etc., etc. And you see in STM, large Coulomb blockade, basically large on-site repulsion. These are experiments started by Yazdani, but Nach Berge and other people now see them also. Moreover, there's experiments which compute or measure really through the Maxwell's relations the spin entropy, and these experiments basically see the appearance of loosely coupled local moments at higher temperatures, and for example the increase in resistivity at higher temperatures, etc., etc. So So experiments which basically see clear local physics, and of course there's experiments that see itinerant physics, which is metallicity, superconductivity, Landau fans, Chern insulators, etc. So there's clearly experiments which show that there's carriers, there's itinerant carriers, and there's loosely coupled moments. Now, there's an abstract of a famous paper in the field which basically summarizes this problem, says that the correlated state features, unusual combinations of contradictory properties, some associated with itinerant and some associated itinerant electrons, some associated with localized moments. So if we're to take this at face value, we would think of the twisted bilayer, some sort of a local moment coupled to some sort of itinerant electrons. Right? And this immediately would give heavy fermion model. However, we cannot do that, as I said, because the bands, these flat bands in twisted bilayer graphene, are actually topological. In that sense, we cannot just map them to a usual heavy fermion model where the heavy fermions are actually highly localized moments. They're basically F electrons, localized F electrons, and their Vanier state would be very localized. If we could map them to that, then we would get no topology, because we know topology is the obstruction to having exponentially localized Vanier states. So a immediate mapping of these problems to a heavy fermion fails because topology exists, and the heavy fermion problem, as in the old Anderson model, etc., doesn't have topology in it. Certainly the flat F electron bands levels are highly localized and they don't form topological bands. So how do we get out of this conundrum? And please interrupt me if there's any questions as I go along this, because it's going to get more mathematical very soon. So hopefully I can get the idea through at the beginning. I claim that there is a principle that maps these flat bands into a topological heavy fermion problem with a model that's Anderson model plus extra terms. And this comes from several observations. First observation that I don't have time to prove is that most exact flat bands that come from finite hopping are topological. Now, not all of them, but there's a principle which you can find in this paper that basically shows you that it's very natural for flat bands that come out of quantum interference, i.e. Wave function interference that basically flattens the dispersion, to be topological. Now, of course, these heavy F electron bands, for example, that have no hopping, where the electrons are very localized, this would be trivial and would not enter here because they would have zero or very small hopping. But if you have hopping between lattice sites, etc., and somehow you get a flat band out of this finite large hopping problem, this, for example, is the Lieb lattice, any line graph lattice, any bipartite lattice with different number of sites, Kagome, for example. These bands have a high probability of being topological because of reasons that I cannot explain in a finite amount of time right now, but that are very well understood. So, as a corollary, when you've got flat bands that come from quantum interference, they tend to be topological. So you cannot write down a heavy fermion model of them, or you cannot express them in localized orbitals. However, what you notice is that unlike Landau levels, and a lot of people associate flat bands with Landau levels, and I want to stress the point that this is not true for flat bands that come from lattices. And this point is made a lot of times in talks, but it's what I believe to be misleading a little bit. The topology of these flat bands comes from basically Berry phases, Berry curvature, etc. Sometimes it's not just Chern number, sometimes it's more evolved, like in twisted bilayer graphing. But the moral of the story is that the topology comes from Berry phases, and these Berry phases are actually concentrated in the Brillouin zone. They're very unlike Landau levels, where the Berry phase is uniform. For example, in momentum space, Landau level has the property that you have uniform magnetic field basically. Now in these cases, when you have topology on a lattice, the Berry curvature actually is concentrated at points. And there's a very simple reason for that. We know that band topology comes from band inversion, okay? When you invert bands from the atomic limits to make them topological. And because you've inverted bands, then all the Berry curvature, or most of it, tends to be localized around the momentum space points where the band inversion has occurred. For example, in graphene, in twisted bilayer graphene, this is a plot of the Berry, of some non-abelian Berry curvature, really. And you can see that it's clearly localized around the gamma point of the Moiré unit cell, and not around the K points, where the emphasis of a lot of theories are, the K and K prime points of the Moiré unit cell. There's nothing happening there. All the topology is around the gamma point. So now,
may I have a question
yes.
here? So
Sure.
if there is C2T symmetry, the Berry curvature is 0, right?
Yeah, this is a non-abelian one. The non-abelian one is not 0. The Berry curvature is
but then how you plot the non-abelian Berry curvature?
Well,
it's a matrix, right? Something like.
Yeah, but only the off diagonal part is important. Okay, so this is some A. Okay, and then it's basically the Berry curvature of this A, of the off diagonal one.
Okay, but then there are many off diagonal elements in that.
There's only 2 because there's only 2 bands here.
Oh, I see. You only look at the per valley per spin for the central.
Right.
Okay.
Right. In generally, when you have a larger matrix, you might have to take Frobenius norms or some other quantity. But in this case, it's very simple because they're just 2 bands.
Okay, I see.
Thank you.
Thanks.
Good point. Okay, yeah. So basically, you can see that all the Berry curvature is concentrated here. Away from these gamma points, there's no Berry. Well, again, as was pointed out by Fan, is not really a Berry curvature. Some off diagonal part is some non-abelian part of it. But you can see that away from the gamma point, there's nothing. And hence, this means if I don't have any Berry phases, it means I can basically Wannierize the system. So I can Wannierize all these states in the 2 bands per valley per spin of twisted bilayer graphene. I can Wannierize them and make localized orbitals with the exception of the gamma point. So away from these Berry hotspots, the flat bands can be Wannierized, and you can find local orbitals. But these hotspots kind of mess up the Wannierization to find local orbitals and to express the system in terms of a local orbital system. So what you do is the following. You can take a topological band and kind of trade off its topology for a topological semi-metal. So you can express, and this is point 4, a topological flat band as the trivial localized flat bands coupled to a topological semi-metal or topological metal. And the topology is now pawned off, is now put onto the semi-metal. When you couple this trivial localized band, most of the Brion zone has no Berry phase. I can localize it. I can make local orbitals. Once I get rid of the Berry curvature or Berry phases around the gamma point by putting them onto the semi-metal, I can localize the entire I can localize the entire flat band over the entire Brion zone. But now the price I'm paying is that I have a coupling to a topological semi-metal, which picks up the Berry curvature and the topology of the system. So after I couple them together, I get the same bands as previously. But now I get the advantage that I've managed to bring in local orbitals and a semi-metal or some metal which carries the topology. So I separated my degrees of freedom. Now, why is this good? Well, the reason why this is good is that there's degrees of freedom that are now localized, the trivial flat band that's now localized, that couples to the topological semi-metal to give the topological flat band in the end. This flat band, this trivial flat band, will carry all the interaction, and we'll see this in twisted bilayer. So now you can think of this as a Kondo or heavy fermion model, where I have a flat band of localized orbitals carrying all the interaction that is now coupled to a topological semi-metal. Because of this topology, etc., you're going to get extra terms in the Anderson model that in the interacting Anderson model that you're going to write down at the end, that comes out by calculation. And these extra terms are density between between the localized and delocalized electrons, and there's some Hans terms that also appear, as I'll show. Okay, so now this was basically the message of the talk, and the rest is details, which are more mathematical. So I'm going to go through them very fast. So this is what happens in twisted bilayer graphene. I showed you these bands. Okay, they have some representations these are 2 per valley per spin. Now the Hubbard U is likely of the same orders as the distance, as the energy difference between the flat band and this set of dispersive bands. And by just doing some simple check on a website that we built a long time ago, a few years ago, with our collaboration in Spain on the Bilbao crystallographic server, you can check that the bands, the flat bands at around charge neutrality, 2 per valley per spin, have to be topological. And you can ask what kind of topology there is. I'm not going to go through it in much detail. There was a lot of controversy between different groups, or maybe not controversy, but back and forth between different groups. It turns out that topology is, if you keep all the symmetries of the model that characterizes twisted bilayer graphene, which is this Bismuth-McDonald model, if you keep all the symmetries of this model, topology is actually stable, and is stable, as we pointed out at the very beginning, is stable. Stability has to do with the existence of 4n plus 2 Dirac points. So remember that there's a Dirac point at the K Moiré, there's a Dirac point at the K prime Moiré. These are both, this is the K Moiré, this is the K prime Moiré, this is both in one valley. These Dirac points are 2. Everything else with these symmetries has to come in 4 plus n. So just remember the topology basically is equivalent to the existence of 2 Dirac points in any set of bands that you take in the Bismuth-McDonald Hamiltonian. Now, in order to get this construction of the heavy fermion for twisted bilayer, we first have to build the localized states. And as I said, these bands are topological, so you cannot build localized states just out of them. But if you look immediately at the next set of bands and at the Berry curvature is concentrated around gamma. If you look immediately at the next set of bands, you see that the next set of bands actually have a representation. This is called gamma 3 on the Bilbao crystallograph, so you don't need to burden your brain with these labels. But if you just would borrow that representation, you would immediately see that there is a localized atomic orbital limit that you can build with the representations of the flat bands at every point but the gamma point, and borrowing the representation at the gamma point is gamma 3 of the dispersive bands. And this atomic limit is, lo and behold, on the triangular lattice, exactly where the STM sees these. So what we do is we actually build trial states of these Vanier states on a triangular lattice, and we then project them using Vanier 90 on these 6 bands within some energy window that's basically given by the Hubbard U, flat bands plus minus Hubbard U. We project them onto the 6 bands of Bismuth-McDonald model, and we find extremely localized Vanier states. These Vanier states are spread, their spread is 0.2 the Moiré unit cell. So that means that the hopping between these nearest neighbor Wannier states is basically zero. It's 0.1 milli-electron volts. The bandwidth of the flat bands is 10 milli-electron volts. So basically this is zero. So we found our heavy fermion. Now we ask how much of these flat bands, of these two flat bands per valley per spin, do these heavy fermions localized states contain? We know they cannot contain 100% because the flat bands are topological. So they cannot be fully given by the heavy fermions. We know that these heavy fermions have the wrong representation at the gamma point. They have this gamma 3 and not the gamma 1, gamma 2 representations of the flat bands, which you can see here, gamma 1, gamma 2 of the flat bands. They don't have this, so they cannot be 100%. But when you compute how much they make up 96% of the flat bands. And hence they make a lot of the flat bands are given by these heavy fermions. Now, what are the remaining 4% states? Because of lack of time, I'm not going to show you the proof, but you can go through a proof, you can derive them also by symmetry arguments, etc. But basically, what you find is that the remaining 4 states can be written down as an untwisted AB bilayer graphene fermion, which has a quadratic touching at the gamma point, right? If I just look at the untwisted AB Bernal stacked, I see in one valley, I see a quadratic touching, okay? And this quadratic touching is equivalent to 2 linear touchings. So this is, remember, I told you that there's this 4n plus 2 Dirac points, topologically is the same. So basically, this is what carries the topology. The conduction electron is basically, there's 4 bands of the conduction electron with a double vortex at the gamma point, and this carries the topology. And this Hamiltonian is very simple. It has this mass term, which is basically this difference between the gamma 1 and gamma 2 eigenvalues. In bilayer graphene, it would be hundreds of electron volts, but here it's actually much smaller. You can see it's around 4 milli-electron volts, and this is just the bandwidth of the Bismuth-McDonald's. It's just this bandwidth of the Bismuth-McDonald Hamiltonians. Now we have the remaining states, and the physics is that of having a localized F electron on, we call it F electron. It's actually by symmetries, P plus I.
So Andrei, may I have a question here?
Yes.
Yeah, in broader bilayer graphene, if you have this so-called triangular warping that keeps the threefold rotational symmetry, the quadratic band touching will split into 4 Dirac points instead of 2.
Right.
But in twisted bilayer graphene case, there is also a threefold rotational symmetry. Then why it splits into 2 instead of 4?
So this is no splitting right now. I can consider extra terms and I can consider extra terms and make it split. But here, actually, there's a symmetry that keeps, there's an extra symmetry here, which is a particle hole, okay, which keeps this representation to be twofold, to be gamma 3, to be twofold generate. And if with the symmetries are a bit different here, there's an extra symmetry that starts.
Okay, then the split Dirac point must be at the K point, I guess. To maintain
so this one is no trigonal warping, etc. Right? It's
I understand, but eventually,
if I add trigonal warping or whatever, if I add extra terms, I still don't think this one would there could be other that would appear, but I still don't think this one would split. I don't fully know, but I can look into it. But I don't think this one will split just because the symmetries are slightly different here. You get an extra particle hole that basically I think will keep this at the gamma point. The K point is irrelevant here anymore, right? The K point is just localized now. So I think the issue is that there's an extra symmetry in this Bismuth-McDonald model, which is this particle hole, which makes, now if you break it, then of course, you can split it into Dirac nodes as long as the sum of them is 2, right? The sum of their chiralities is 2. That's the only thing that's really, if I break this particle hole, that's the only thing that remains. Just like in bilayer, right? If I split them into 3 plus 1, but the one has the opposite chirality, so it's still a double vortex if I take right?
Okay.
Very good, thank you. Right, so the physics I claim is that of an F electron on the triangular lattice coupled to an AB untwisted bilayer graphene conduction electron that basically lives mostly around the AB part of the Moiré lattice. Now, the coupling between them is very simple because these representations at the gamma point of the C electron or the F electron are the same. They're still gamma 3. And hence, the coupling between them at the lowest order is just identity times a value gamma, which is the largest energy scale in the problem up to now. So what we can ask now is, how well does this model reproduce the Bismuth-McDonald-Hamiltonian? The Bismuth-McDonald-Hamiltonian is a continuum Hamiltonian. It's got a lot of shells. I need to, take out to build it on a 90 by 90, 100 by 100 lattice to get convergence, blah, blah, whatever. This model is 6 by 6, okay? And this is the model that these are the F electrons, these are the C electrons, okay? And we can ask how well does it reproduce the Bismuth-McDonald model? And this is how well it reproduces it. The red dots are the Bismuth-McDonald models, the black lines are this model. Now, of course, at higher energies, it doesn't reproduce the Bismuth-McDonald model because, well, it would reproduce it if you would add extra terms in this model, etc. But it doesn't reproduce it very well at higher energies. But you don't care about higher energies because the Hubbard U certainly cannot cause excitations from these higher energies. So all you care is with energies within the Hubbard U, and you can see how well it matches the Bismuth-McDonald model at low energies within plus minus Hubbard U. And you can now understand that this mass term here, M, or twice times M, is just the bandwidth of the Bismuth-McDonald model. This coupling between the F and C electrons, gamma, is just the gap between the flat bands and the dispersive bands, etc., and so on. So now I claim that we have an a single particle model that's heavy fermions coupled to a topological semi-metal, which is this double vortex, or it can split in other vortices as Fan was mentioning, but at the simplest form is just a double vortex. And now we can ask what is the interacting model, and we can calculate it. And what we find is that the largest interaction is that between the F electrons, as we expected, is around 60 milli-electron volts. In STM experiments, is usually what usually is quoted is U over 2, around 30. This is the largest interaction in the model, and an extra term that appears that's not just like the Anderson model is a Hans coupling between the F electrons, or the localized electrons, and this conduction electrons. And now I'm going to argue that the physics of these systems in probably 5 minutes is very easy to understand, because all you want to do now is to polarize the F electrons so that you save this Hubbard energy. Once you polarize the F electrons, so you save this Hubbard energy, the F electrons are going to have a density matrix, some sort of an expectation value. This expectation value will enter here in this Hans coupling between the F and the C electrons. They will create a mass for the C electrons, which will gap the double vortex. But we know what happens when you gap either a Dirac fermion, which is a single vortex, or a double vortex. You create Hall conductance, and hence you can get Chern insulators, etc. So I wanted to also point out that, at the beginning we only found these numerically, but now these values of these parameters can be found analytically, and this will appear soon in work with Pierce's group. Okay, so now this Hans coupling looks a little bit intimidating, okay, but actually is quite simple in the sense that it can be written down as a real Hans coupling, but not between an SU2 spin, but between a U4 spin. So in what's the flat limit of this model, which we call M equals to 0, M is basically very small. If we put it to 0, we find out that we have a U4 symmetry of the full interacting and one-body Hamiltonian. There's the U4 operator that commutes with it. And in this U4 symmetry, the Hans coupling is a spin of the f electrons times spin of the c electrons, but U4 spin. And there's actually two U4 spins. There's 8 f electrons. There's 2 per value per spin, 8 f electrons. So there's 2 basically U4 spins per site, per AA site. And this is now easy to interpret. It's just the Hans interaction between the f and c electrons. Now, at integer filling, what you want to do is you want to fill the f electrons. The f electrons have a lot of Hubbard U. You want to minimize it, so you want to polarize them and fill them like in a ferromagnet. And the filling is hence controlled by the f electrons. But then you can ask, there's 8 of them, value and spin. How exactly do you fill them? Which value is spin? And it turns out that you can prove a Hans rule for the f electrons themselves. And the way to prove it is actually very tedious. It's something that will come out with Hu and Alexei Zvelik, that basically you integrate out the conduction electrons and obtain interactions between the f electrons. And then what you find out is that the way to fill them is also satisfying a Hans rule, is basically 2 f electrons tend to occupy one flavor of this U4 symmetry. It's a Hans rule of this U4 symmetry rather than of a U2 symmetry. Okay, so let's now understand the state at mu equals 0. The state at mu equals 0, 0 filling, I have to fill 4 electrons. I fill 4 f electrons times the Fermi C of the gapless double vortex. These 4 electrons are filled in some representation, which is Hans rule. Okay, and this is the trial state. And now you run Hartree-Fock. Turns out, because the separation of energy scales is so good, one-shot Hartree-Fock is as good as self-consistent. What happens is that the f electrons polarized by Hubbard U, okay, they create these Hubbard bands here of f electrons. Now, the FC splitting causes level repulsion here, which makes these bands come down. And the J term opens a gap here. This is basically the Hans rule, the Hans coupling between the f and the c electrons opens a gap here due to the fact that the f electrons have polarized, created a density matrix, which self-consistently feeds into the coupling between the f and the c electrons. Now I've opened the gap here. Since this was a double vortex, I created a Chern number. And now whether the state has an overall Chern number is given by whether the Chern numbers per value per spin sum up to 0 or non-zero. So there's a formula that you have. Turns out that it's filling at odd filling, for example, at filling 1, the only option is a Chern number 1 if you don't break the translational symmetry. And this was seen in Efetov's experiments where they see a Chern number 1 and filling 1 minus 1. Okay, so now I think I've went over my time, but I wanted to point out that this model, this is upcoming work we just started, is also very well suited for DMFT. And in effect, what you see in DMFT is that at integer filling, the electrons do obey a Curie law, so there's local moments. However, if you go away from integer filling, you see deviations from the Curie law, and you basically see some sort of Kondo screening starting to happen, and this is clearly shown here, where you plot T times the susceptibility for different fillings. And some more interesting aspects of the STM data, such as what are tail feathers in Alice, there's an experiment might be actually explainable by Kondo resonances of these local spins at the Fermi level. Now, I want to point out that you can do the same for twisted trilayers. This is again not published, but this heavy fermion formalism works extremely well in the sense that you cannot see the difference here between the Bismuth-McDonald Hamiltonian for trilayers and the heavy fermion, where one is blue, one is red. They're almost on top of each other, even with displacement field. And in the last slide, I wanted to point out, I've said that this is a generic paradigm, so I wanted to point out 2 other cases where this is also true. For example, Hong Yao has a model of the checkerboard lattice, twisted checkerboard lattice. And in this twisted checkerboard lattice, actually, the Berry curvature is the same C2T Berry curvature as in non-abelian one as in graphene. It's concentrated around the X points, not around the gamma point. But again, you can build a heavy fermion model of it, and you find out that most of these bands, as you can see here by the size of the blue dots, most of the flat bands are actually heavy fermion, and this model can reproduce the band structure very well and the interacting spectrum. Now, even more more clearly, the case of the Lieb lattice has the band structure has a flat band but has a degenerate point. So in this case, you can never just project an interaction to the flat band because you have gapless excitations around it. So but what you can do is you can do the same heavy fermion formalism and write most of the flat band, as you can see here, most of it as a heavy fermion. We know where it's localized, but I don't have time to go through it, coupled to a Dirac semi-metal. And this again can lead you to the interacting states on the Lieb lattice. Now, these are, of course, theoretical. So basically, this is what I wanted to show you. I wanted to make the case. Most of it this is unpublished, but I wanted to make the case that when you've got an interaction that's as large as the distance between a flat band that comes out of interference and a dispersive band, then there's a paradigm, which is a topological heavy fermion paradigm, that can separate the degrees of freedom into localized ones that carry the interaction and delocalized ones that carry the itineracy. So with that, I thank you.
Thank you very much, Andrei, for the great talk. Now we open for Q&A. If you have questions, please raise your hand. I will call your name according to the order appearing my screen. Let's see. Okay, maybe I can start with one from a non-expert point of view. So the methodology or paradigm you developed here, I'm wondering for experimentalists, do you have any kind of implication for understanding the the experimental phenomenon, for example, those STM results observed by Ali, or predict some other experiments?
Right.
Yeah.
So I mean, so I'm not sure if I have here the Ali spectrum, but for example, right, they see at starting from integer fillings, they see these resonances that basically follow the Fermi level, and that what we claim basically and are basically the Kondo resonance of these spins. Obviously, we also claim that these Andrei Young and Shahalilani experiments, where you basically see loosely coupled moments. So you basically you kind of raise the temperature and the moments unfreeze. This is exactly the fact that at low temperature you have a Kondo state, and at higher temperature you have localized moments. So what we claim is that, of course, it can explain a lot of these, and it's a natural explanation of a lot of these phenomena. And of course, these things like linear resistivity that in Efetov's experiments are now seen over decades of I think 2 orders of magnitude in temperature. These ones are not very easily explainable without some sort of a heavy fermion formalism. So I think there's a lot of clear there's a clear case to be made that in experiments that there is a separation of scales between localized or there's both localized and delocalized degrees of freedom, and I think this is the explanation. Now, predictions, of course, would be heavy fermion exponents, etc. But then one would need to look in more detail, where in the phase diagram these predictions are.
Great, Thanks for the insight. I have one
May
more
I have
question.
one more question, Andrei? So I missed the last part of talk. So is that possible to generalize this kind of idea to, let's say, ABC stacked multilayer graphene with the boron nitride?
Oh, with boron nitride, yeah. So I mean, so if I have ABC stack, not you don't mean twisted.
Yeah, I mean twist with the boron nitride. Yeah.
Oh, okay. Yeah. So this is so untwisted, and I see Ming is online actually too. And untwist, if I have twisted trilayers, for example, and then this has already been done. It hasn't been published yet, but so if I now want to add a substrate, all I need to do is to couple these heavy fermions to the substrate. Now there are cases where the formalism will fail. So for example, the reason why the formalism is very good here is that this coupling between the F and the C electrons, gamma, is 20 milli-electron volts, is much smaller than U. See, this is usually when the heavy fermion formalism works. If I want a separation of scales that my heavy electrons, my localized electrons, coupled to my conduction electrons with a hybridization that's smaller than the Hubbard U, then I have a reason to make a separation of scales, because
I see.
But if gamma is much larger than U, which is incidentally what happens in this case in the chiral limit. In the chiral limit, that it's an unrealistic limit. It doesn't happen in twisted bilayer graphene. But in the chiral limit, gamma is much larger than U. So then a heavy fermion formalism would not be very useful. But so of course, it's not a painted brush that you can just use all the time. But I argue that for most flat bands, one should be able to use it. So I think coupling to a substrate would, as long as the coupling is not strong, would it's just a simple generalization of this formalism.
Okay, thanks. I think there is a question, from the chat.
Right. So, Ming, do you have a question? You can now raise your hand as a co-host.
Yes, thank you, Andrei. Thank you very much. Can I ask a question regarding how much of an analogy we can carry with the heavy fermion, in the sense that when we look at F-band and the heavy fermion, traditional heavy fermion, the spectral weight is actually, the coherent spectral weight is actually very small. Most of it is in the incoherent sector. So in the geometrically frustrated flatband systems, how can you, is it also the same case here, that would you be able to observe these spectrally, or there's additional degree of correlation effects that can be added into to further suppress the spectral weight?
Right. So I think yes, it's very good. So I think basically so related to this, for example, is the question why do I claim that these Hartree-Fock are so good, right? There's at least at the integer fittings, there's heavy fermion. It's a complicated system. The one thing that's different from the heavy fermion is that you see the conduction electrons have very low density of states, at least at integer fillings. At integer fillings, basically the F electrons get filled, and the conduction electrons have very low density of states. Because of this will actually just give order states at integer filling, ferromagnetic states. At integer filling, you shouldn't expect Kondo screening. Now, because there's just linear density of states almost. There's a quadratic component here, but it's very small. So this is why actually this works very well at integer filling standard. Now, as I go towards as I start doping the system away from integer filling, so 1.5 or 2.5, whatever, etc., I should start getting some heavy broadening of the spectrum, some incoherent spectral, etc. So that's something that right now we're looking into in DMFT. So I don't have, but it's certainly, experiments do see, at non-integer fillings, strong correlation effects, right? So I don't have a prediction at non-integer fittings so far, because we're just the problem is much more complicated in there, because it's really kind of, it's as complicated, even more because of these extra terms, as a Kondo problem. And this is what we're looking into right now with our DMHT collaborators. I don't think that answers your question really, but that's all I can say so far.
Thank you.
Thank you.
Thank you. We should probably